We are once again peering into the algal forests of a riverbed. And in such a rich environment, there is always more to be discovered. Not just new species, but new ways to view them, new ways to appreciate the beauty of the microstory. And one of the first things I have come across is the skeleton of a Daphnia. And right beside it, gleaming like a living jewel, the shell of the freshwater diatom, Stauroneis. Diatoms are surrounded by silicate shells, and they have appropriately been called living jewels because their shells are made of hydrated silica, the same material as that found in opals. But as beautiful as their shells are, that is not the subject of my interest. Not today. What I am interested in is what is within. Because as we peer closer into the diatom, we can see the living, breathing, green stuff of life. Like all eukaryotes, diatoms have various organelles, including chloroplasts, which are the organelles that allow diatoms to conduct photosynthesis. In this, diatoms are similar to plants, though they acquired their chloroplasts in different ways. Applying a false color technique I call double green fluorescence, I am amplifying only the green channel of the camera's color CMOS. This allows us to eliminate challenges with focusing other colors, giving us the clearest possible view of the life activities within the diatom structure. Right beside the Stauroneis diatom is yet another, known as cyclotella. Because it is so tiny, to see it sharply I will apply a technique similar to that I used last time, ruling out the undesired colors of light, amplifying luminosity contrast, and superimposing the color band on top of that. This allows us to see the life processes of cyclotella even at an effective 900 magnification without oil. Over the previous episodes, we've looked at other diatoms as well, such as my favorite, Closterium, which forms the logo of this channel due to its beautiful crescent shape and its lovely green colors. But I've always been especially fond of diatoms. Not only are they beautiful, but they are absolutely essential, forming a foundation of the food web and providing so much of Earth's oxygen. I really think these organisms, so much like plants and not, deserve more attention. Returning our attention to the algal forest, it is not too long till we find a bit of filamentous algae. Filamentous algae can reproduce by spores, but also by breaking up into fragments like this. Nearby, we find the beautiful spherical form of Pandorina algae. This algae is a group of 8, 16, or 32 cells that form a globular colony by connecting themselves via mucilage. Let's take a look at them up close. These are their individual algal cells. Pandorina show the first faltering steps towards cellular differentiation, just beginning their journey toward multicellularity. And here again is our old friend the gastrotich, the hairy belly. Fascinating little multicellular animals found in rivers, lakes, streams, ponds, and the oceans. These are very successful creatures, and there are quite a few species of them, some 800 around the world. Gastrotrichs are active organisms, and while I've developed some technique for tracking moving organisms under the microscope, they completely manage to challenge the best of my abilities to keep them center stage, moving at the speed of race cars on the microscopic scale, and making random sudden turns at any given moment. Gastrotrichs are generally easy to find within the periphyton. That's the slime that one would often find on rocks and pebbles at the floor of water bodies, though some species can be found on land, living in the thin film of water between particles of dirt. They move fast and they live fast. Gastrotrichs have lifespans of only a few days. But following this gastrotrich led to a lucky break, and today's star of the show. For in following the gastrotrich, we've come across a Hypotrich. Despite the similarity in the sound of the names, these are not related organisms. For starters, Hypotrichs are single-celled protozoa, whereas gastrotrichs are multicellular animals. Though visually, they might appear a little similar, they can be nearly of the same size, and they both appear to have cilia. But the cilia of the Hypotrich are quite different from that of the gastrotrich. They have compound ciliated organelles, essentially fusing a number of cilia together into cirri. You might think of cirri as much more substantial cilia. Put simply, thicker hairs, except it's not so simple as that, because Hypotrichs, as per their name, do in fact have a trick. Many of them use their cilia almost like primitive legs, appearing to walk on whatever surface they happen to be on, looking a lot like little animals. Like the microanimals that have a similar name, Gastrotrix, Hypotrichs are busy little creatures. They never seem to stop moving, though I would describe their movements, at least the movements of this one, as more graceful and fluid, easier to follow around on the microscope slide. Hypotrichs are of scientific interest for many reasons, one of which is that they're cirri, their thick and unusual hair-like structures, as well as their widely diverse body formats, provide clues into how many ciliated organisms evolved. Scientists have also described them as a somewhat frustrating branch of organisms, because their widely diverse morphologies, or body types, leads to them often being confused with other genera. And because of this, various organisms are occasionally added to, or even removed from, the Hypotrich classification. But, as a documentarian of the microscopic world, I find there to be something incredibly remarkable about the Hypotrichs. At least this Hypotrich. Looking within its cellular structure, you can see it's busy inside. There are lots of organelles and lots of bits that may be absorbed food. And there are lots of other things. I don't know what. But what do you think might happen if we applied some of the same light manipulation techniques we applied to the Stauroneis, or the cyclotella diatoms from earlier? Remember, diatoms are surrounded by shells that are made of the very same thing that opals are made from. And changing the characteristics of the light that shines over them can do an awful lot to bring out their detail and beauty. But if I take those techniques even further, and widely divide the red, green, blue, and luminance channels of a CMOS sensor, I can induce, how shall I put it, a false true fluorescence within the Hypotrich. A fluorescence which simply plays on the Hypotrich's natural yet subdued colors. And in the doing, I can bring out an amazing hidden beauty of this simple creature. Who would have thought that the humble Hypotrich hid so much beauty? It is a veritable living prism. But that's the microstory for you. Everywhere you turn, there's another wonder, another beauty, another way to be amazed. Thank you for coming along on this voyage of discovery into the microstory. The MICROSTORY program is part of the Understory Network, a group of channels devoted to providing education on the science of the natural world. On our MICROSTORY channel, you can find all of our programs related to all things microscopic. On the Understory channel, we study animals, plants, and fungi, as well as issues related to conservation. And on the Sky Story channel, we explore the world of astronomy and that of astrophotography. Our programs are made possible by our many viewers, patrons, and students. And we owe all of you a profound thanks. And if you like what you see here, please take a moment to like and subscribe.